Chemical equilibrium is a really fundamental unit. We're going to be using these concepts in equilibrium, obviously, but also in acid-base, thermodynamics, and electrochemistry. So it's really important to get a good foundation in this unit. We're going to talk about everything that you need to know, starting with what is equilibrium and how do you solve for KEQ. We'll look at how to use an ice table as a problem-solving tool, and then finally, how to represent changes in equilibrium via the Chatliers Principle and the reaction quotient Q. So let's get started.
In today's video, we're talking about equilibrium. So we're going to define equilibrium and how to solve for KEQ. We'll solve for equilibrium concentration using an ice table. And finally, we'll talk about Le Chatelier's principle and the reaction quotient Q. So let's start defining what it means to be in equilibrium. A reaction is in equilibrium when the rate of the forward reaction is equal to the rate of the reverse. If we're looking at a reaction, A is in equilibrium with B, the rate of the reaction going this way is going to be equal to the rate of the reaction going that way. If we're plotting concentration versus time, the amount of A is constant and the amount of B is constant because the rate of consumption is equal to the rate of production. So there's not going to be any change in concentration, although the reactions are still happening. We're able to write equilibrium constant as a function of the relationship between the products raised to their stoichiometric coefficients divided by the reactants raised to theirs. Let's look at what this actually means. So if we look at this first reaction, I see that my reactants are the C3H8 and the O2, and my products are CO2 and H2O. So I can write an equilibrium expression saying K is equal to my products, CO2, H2O. Carbon dioxide is a gas, and I can see that there are 3 in the reaction stoichiometry, so I would raise it to 3. I see that H2O is actually a liquid, and K needs to have units of concentration, which is mole per liter. This is a liquid, and so if we're thinking about units, it would be moles of water divided by liters of water, which is not concentration. So I actually won't include H2O in my equilibrium expression because I can't have units of molarity with a liquid. This is also true for solids. So we see that equilibrium, no liquid, no solids. Everything else is fine. So I would have my CO2 raised to the third, and then I'm going to divide by my reactant. So C3H8, this is to the 1, so I leave it, and then O2 to the 5th. So at equilibrium, this is describing the ratio of products to reactants. Let's look at another example. In this reaction, I see that my products are N2O5 and O2, but N2O5 is a solid, so I'm not going to include it in my equilibrium expression. I'll just say the concentration of O2 divided by N2O4 times O3. So this would be my equilibrium expression for this reaction. This is really important to practice because every equilibrium problem is going to start by writing a KEQ expression. Let's look at how to solve for equilibrium concentration. We're going to need an ice table and we're going to follow these 3 steps. Again, step 1 is to write an expression for KEQ. So if I'm looking at this reaction, N2 plus O2 makes 2NO. I see that everything is a gas, so I'm going to include everything in my equilibrium expression. I'll say KEQ is equal to my product squared divided by N2 and O2. Here it's asking me what are the equilibrium concentrations. So I'm going to need to make an ice table. I'm going to start by writing my reaction. An ice table is going to be initial, change, equilibrium. I start the reaction with 0.2 molar nitrogen and 0.15 molar O2. At the start, I don't have any NO. I see that these are going to go down, and this is going to go up. I see that for every 1 and 2, I make 2 NO, so this is going to increase in concentration twice as fast. That means at equilibrium, I'm going to have 0.2 minus X, 0.15 minus X, and 2X. This is everything that I need to solve for X. So now I can kind of combine step 1 in step 2. I see my KEQ is equal to 4.1 times 10 to the negative 4. And this is going to be equal to the concentration of NO squared, which is 2x, and then the concentration of N2, which is 0.2 minus x, 0.15 minus x. Now I can solve for x. I see that this KEQ is a pretty small number, which means that I'm going to have mostly reactants and not a lot of products. This tells me that x is small. This change is going to be negligible, so I can ignore it in the reactants. I can continue to simplify this and say 4.1 times 10 to the negative 4 is equal to 4x squared divided by 0.2 times 0.15, which is going to be equal to 0.3. This means that x is going to be equal to 4.1 times 10 to the negative 4 times 0.3 divided by 4, and all of that to the square root. When I solve for x, it's going to give me 5.5 times 10 to the negative 3 molar. So now I can plug this back into here and say at equilibrium, again, this is basically 0.2. This is basically 0.15, and this is going to be 2 times x. So that's going to be 0.011 molar. So these would be my equilibrium concentrations. This ice table we're going to be doing over and over and over again in equilibrium. We're also going to need this in acid-base. So this is going to be a really fundamental skill to practice and learn for basically the rest of general chemistry. Now let's look at what happens when we shift the equilibrium. That's going to be the Chatliers Principle. The Chatliers Principle says a system will respond to changes by trying to reach equilibrium. This means that if I do something to the products, the reactants are going to shift to try to counteract that change. If I do something to the reactant, the products are going to shift to try to counteract that change. We're always trying to get back to equilibrium. Let's look at what this means with some examples. So if I have this reaction, H2 plus Br2 goes to make HBr, I'm going to write a KQ expression. So I'm going to say, okay, K is going to be equal to HBr squared, because the reaction stoichiometry is 2, divided by H2, divided by Br2. And so let's look at what happens when we manipulate this system. If I add H2, I see that the denominator is going to get larger, and so that's going to shift my equilibrium. If I add H2, I'm going to have to shift towards HBr in order to even that out. So I see the concentration of H2 is going to go down. The concentration of Br2 is going to go down. And my product HBr is going to go up. K is a constant, so this stays the same. If I add HBr, the opposite's going to happen. I'm going to have more product than I should have of reactant. So I'm going to see H2 go up, Br2 go up, and HBr go down. Again, K, we're at the same temperature, so it's a constant. If I remove H2, it's like I have a hole. And so the equilibrium needs to shift to fill the hole. I'm going to see these increase, and the HBr is going to decrease. If I make a hole over here, again, the equilibrium has to shift to fill it. So I'm going to see this go down, and I'm going to see HBr increase. K, again, we're at the same temperature, so it stays the same. The temperature is actually interesting. So K is not the same at different temperatures. That's the only time it really changes. And to see the temperature effect, I want to see if the reaction is endo or exothermic. So this delta H is going to tell me that. I see a negative enthalpy, so this is going to tell me that I'm exothermic. This means energy is being released. So I can think about heat as a product in my reaction. So if I'm increasing the temperature, I'm basically increasing the amount of products that I have. So the equilibrium is going to have to shift away from that. That means that H2 is going to go up, Br2 is going to go up, and HBr is going to go down. because I'm shifting to have more reactants, I see that this term in my KEQ expression is going to get larger. This means KEQ is actually going to be smaller at higher temperature. If I decrease the temperature, that means that I'm making a hole here. And so I have to shift to fill the hole. So I'm going to see H2 go down, Br2 go down, and HBr go up. Because I'm increasing the product term in my KEQ expression, I'm going to see that K is actually going to be larger at lower temperature. And so whenever we're looking at temperature, we want to look at whether the reaction is endo or exothermic. Finally, let's look at what happens if we increase the pressure. If we're increasing the pressure, all the particles are going to be closer together. So I want to move to the side that has less gas. Here I see on the reactants, I have 2 moles of gas. Here I see that I also have 2 moles of gas. And so in this situation, there's not one side that has more. There's not one side that has less. So there's going to be no change in the equilibrium. But if I only had like 1 mole of gas and 2 moles of gas, if I increase the pressure, I'd be moving to the side with less gas. If I decrease the pressure, I'd be moving to the side with more gas. So just some things to think about. Let's look at this now mathematically by looking at the reaction quotient Q. So KQ, the equilibrium constant, is for equilibrium specifically. But the reaction quotient Q is for at any point in time. And so we set up Q the exact same way that we set up K. It's going to be the products to their stoichiometric coefficients divided by the reactants to theirs. But here we can solve for this at any point in time. So we don't have to be at equilibrium to find the reaction quotient Q. And this is going to tell us how close we are to equilibrium and what it needs to do in order to reach equilibrium. We can have 3 scenarios here. When Q is equal to K, that means that the reaction is at equilibrium. There's going to be no shift happening. We're already at equilibrium. We can have a situation where Q is less than K. If we're looking at this mathematically, Q being a smaller number means that we have more reactants and not enough products. That means that the reaction is going to shift right in order to reach equilibrium. And if Q is greater than K, if we look at this mathematically, this is going to tell us that we have more products and not enough reactants. So in order to reach equilibrium, we have to shift left in order to make more reactants and get to a place where Q is equal to K. And so we looked at Le Chatliers principle, and let's now combine these two things. So we see that when we added H2, that's going to increase this term. So if we're thinking about Q, here Q is going to be less than K. And so the reaction will have to shift right. And that's what we see following Le Chatliers principle. If we're adding HBr, then the product term is going to increase. Q is going to be larger than K. We'd have to shift to the left. And that's what we see again with Le Chatliers principle. If we're removing H2, we're going to see that this term gets smaller. Q is going to be larger than K. We're going to have to shift to the left. If we remove HBr, we see that Q is going to be smaller than K, and we're going to have to shift to the right. Q is really useful in telling us in which way a reaction will shift. And so we can actually combine that with our ice table in order to find equilibrium concentration. So let's look at this particular problem here. Here, I'm going to start by writing my KEQ expression. So I'll say that K is equal to the concentration of HF squared divided by H2 times F2. Everything is a gas, so it all stays in my equilibrium expression. If I set up my ice table by rewriting my reaction, what I see is that I'm starting with 0.05 mole of all of my reactant. But instead of starting the reaction at 0 product, I'm actually starting at 0.6 product. And so I need to figure out in what ways the reaction going to go. I don't know if I'm going to be minus x here or if I'm going to be minus x here. So that's what we need to figure out. So step 2, I'm actually going to be solving for Q before elaborating my ice table. Q are set up the same exact way as K. So I'm going to say the concentration of HS, which is 0.6 squared, divided by the concentration of H2, which is 0.05, times the concentration of F2, which is the same. So I'm going to say square. This is going to be equal to Q. If I solve this, I get 144. I see 144, which represents Q, is going to be greater than K. So in this case, Q is larger than K. That means I have more products than I should at equilibrium. So the reaction is going to shift to the left. What this means for my ice table is that I'm going to have a minus 2x actually on the product side, and then plus x on my reactant side. So that means that at equilibrium, I'm going to have 0.05 plus x, 0.05 plus x, and 0.6 minus 2x. And so now I can solve for x by plugging into my KEQ expression. So I see that K is equal to 115. So I'll say 115 is equal to the concentration of HF squared divided by the concentration of H2 times the concentration of F2, which is the same. And so mathematically, this gets a little bit more complicated. I see that these are both squares. So I'm going to take the square root of everything to remove those. So I see the square root of 115 is going to be equal to 0.6 minus 2x divided by 0.05 plus x. Now I'm going to cross multiply because I'm trying to isolate x. So here I'll have 0.05 minus x times the square root of 115 is equal to 0.6 minus 2x. If I factor that through, I get square root of 115 times 0.05 minus the square root of 115 times x equal to 0.6 minus 2x. I'm trying to get all my x to the same side, so I'll say the square root of 115 times 0.05 minus 0.6. It's going to be equal to the square root of 115x minus 2x. If I solve for this, I put this all in my calculator. What I see is that x is equal to 0.005 molar. So that means that at equilibrium, I need to plug my x in here. And so I'm going to have an equilibrium concentration of 0.055, 0.055, and then I'm going to have an equilibrium concentration of 0.6 minus 2x. So that's going to be 2 times x would be 0.01, so 0.59 if I can do math correctly. And so these would be our equilibrium concentrations. So today we've looked at K, we've looked at Q, and we've looked at solving for equilibrium concentrations using both K and Q.
Alright, I hope after today's video we have a better understanding of equilibrium. Any questions that you have, drop them down below or visit stepsystem.org for more information.